other is that the universe might have had an origin where everything collapsed to a single point. That is, the universe grew and collapsed back to a single point. We would not be around to observe that, because that single point would have a lot of the features of the early universe that I showed where atoms could not form. That's another structure that could have occurred.
Can I
Sure.
tell you while you're on that slide, where is our galaxy in that spectrum?
Well, this is a cartoon of all galaxies, so it could be anywhere on here. All right, let me see, I'm not sure I understand your question. Right.
Well, from how old we are.
Oh. So our galaxy probably formed here, say, 7 or 8 billion years ago. This goes out to the entire age of the universe, kind of like 13.5 billion. Our galaxy is not among the oldest.
Then I had another question while you're on this. If we have no central point, what would the Big Bang point where this is kind of in that?
Where did it happen?
Uh-huh.
It happened everywhere. I'm sorry. See, here's I want to alert you to when professionals have conversations about these things, they do not use human language. They use mathematics. But if you force them to have a conversation about this, they say, the Big Bang happened everywhere at the same time in an incredibly small place. That place, that universe, which was smaller than an electron, has gotten enormously big. On a human scale, it's enormously big. But it's getting big everywhere at the same time. This is some of what I have to tell you during these meetings is a little mind-bending. But the universe was born all at the same time everywhere. And it's gotten bigger and cooler. Good for us because it gave us a chance to evolve. I know that's unsatisfactory,
No, that's
but
good.
I will say again, when the professionals get together to talk about some of what we will discuss, actually I have a quote on this from, how many people have read a Brian Greene book? Okay, so there's a little quote from Brian Greene having to do with the geometry of the universe, which we will discuss. And he said, you know, folks, when we get into the topic of the geometry of the universe, and various ways it could turn into the shape and so forth, professionals have long since understood you can't have a conversation in the English language or any other language. We have to go to equations. So it's a challenge from an educational point of view of how to convey this. But I'll reassert it. The universe began everywhere at the same time in an infinitesimally small place that is now much bigger, and it's all evolving everywhere all the time. And it's big now. It's 13.7, so we should say this too. As this 13.7 billion years of evolution means that the most distant objects are receding from us at the speed of light. Anything that's going away from us faster than the speed of light, we don't see it anymore. That's called the horizon. We can't see anything beyond the horizon. And there's stuff out there. I'll explain why we know that's true. There's stuff in our universe that we cannot see because it's receding from us, not because the objects are moving through space faster than the speed of light, which would violate a fundamental principle, but space is expanding faster than the speed of light. And every observer in the universe has the same experience. Everything is going away from me. We'll talk about that probably pretty soon. So, 100 billion galaxies with 100 billion stars. That's a big number. There's supposed to be 22 zeros in that. That's more than there are grains of sand on our planet. So we've already talked about this. Oh yeah, we should have mentioned a kind of a thing you can keep in mind is the time it takes light to get from the sun to our planet, around 9 minutes. galaxy is 200,000 light years in diameter. Of course, we've never seen our galaxy. We'd have to be outside of it to take a picture of it. But we can observe stars in our galaxy and their motion, and we understand the rotation rate, and lots is known. Yes?
So are the galaxies expanding like the universe is expanding?
Oh, I'm so glad you asked that question. I'm going to show you a little video that explains this. Let me see when that comes up. Okay, so we're going to have a little technical interlude. How are people doing? Does anybody need a break? We've been doing this for an hour. Break necessary? No? I'm okay. So at some point, somebody will, Pam, who's actually in charge, will
I was
take.
gonna say, we probably should take a small break now,
Okay.
and I had a couple of announcements for the class.
Oh, good. So, all right, let us do take a break.
If everybody has signed in on the attendee sheet, I'll pick it up after this break. If you're not on the sheet, please just write your name down on it. Caps on all the drinks, silent cell phones, which none have gone off, so that's a good thing. And there is the first, was it Midday Morsels, is going to take place next Tuesday, the 21st, at First Universalist Church at 11:45, and it's a town hall meeting with Executive Director Barb Radcliffe. She'll be discussing the vision of Ollie at DU and the 2025 plan. And then one final thing, we follow the Denver Public Schools snow cancellation policy. If they cancel, we're closed. If they're late, we're on time. But there was a problem in the fall where DPS opened and DU closed. And so even if you see DPS open, you might want to check and make sure DU is open as well. That's all.
Okay? So if other people don't want to take a break, you can get up and leave anytime, of course. But I just as soon keep going, because I've been going a little too slow, I realize. So there's a sort of number of these slides I want to get through today. I'm going to pick up the pace a little bit, so we're trying to land at the end of the presentation when we get to 2 hours. Yes?
I think it might be helpful to dim the lights a little bit.
Oh, sure.
For your presentation, too.
Oh, okay. Let's see, how about, is that okay for people?
It's good.
Oh, okay, good. And it's a good time we did this, because we're going to talk about one of the most important tools in observing the cosmos, which is spectroscopy. So you've all had this experience of picking up a triangular piece of glass and seeing different colors, or looking at a compact disc, music disc or something tilted around, you see that white light is made up of a spectrum of colors. And that's a very powerful tool in observing stars and galaxies. So if we look at this drawing, each of these blue lines is associated with a particular atom. It's like a fingerprint. For example, hydrogen, these are distributed in wavelength or color. So hydrogen has an interesting pattern. It's the structure of hydrogen, the simplest atom, has energy levels distributed like this. So this blue line, and this one, and this one, and this one, and so forth, are all associated with hydrogen. This one, and this one, and this one, and this one are associated with helium. And oxygen is here, there's two together, and so forth. Neon, ionized neon is here. Observations started in maybe the early 1800s, looking at stars, particularly our sun, revealed a pattern that matched what was seen in a laboratory. So you could, even back then, they could produce ionized oxygen, for example, and look at its spectral properties, and then point a telescope at the sun and noticed, hey, we see that fingerprint, there's oxygen on the sun, there's carbon on the sun. And they found one they had not seen on Earth, and they assigned the name helium to it. The Greek word for the sun is helios. So helium was found on the sun before it was found on Earth, because it's in the atmosphere, but it's in very small quantities. And so spectroscopic detection of elements allows us to determine the composition of stars and galaxies. So here's helium. That's its spectrum. Sodium here, neon, mostly in the red. And this is what a galaxy looks like. All kinds of elements are identified in galaxies, and we can tell all sorts of things about the structure of galaxies by looking at their chemical composition. Because the same chemicals that exist on Earth exist on these distant galaxies. Now, there's another feature of spectroscopy that is exploited, and that is revolves around something we've all heard. If you stop at a railroad crossing as the train approaches and they blow the whistle, you hear a certain pitch. And as the train or an ambulance or something goes by, you hear that pitch change. It's called the Doppler effect, because the source of the sound is moving. And in front of the train, the sound is compressed, and behind the train, it's stretched out. The same thing happens for light. So here's in the laboratory, we measure the spectrum of something. Let's say that's helium. If we look at helium in an object that's moving away from us, we see the same spectrum, same spacing, but it's shifted. It's shifted toward the red. The object's moving away from us. If it's moving even faster, it's shifted even farther. So you'll see that this blue line here, in this depiction, well, actually, this one, that blue now appears green, and this green appears yellow, and this red is becoming more difficult to see. It's in the infrared. If something's moving toward us, this spectrum now shifts to the left, and this blue line becomes more blue, and this green is approaching blue, and this red is starting to look orange. So by looking at the spectral shifts, we can tell the velocity of objects moving toward or away from us. This is enormously important, as you will see in a second. There is yet another feature of this whole process of looking at objects, and that is to build a so-called cosmic ladder. So if we want to study the moons of Jupiter, we can use radar. We can produce a signal, send it out, bounce it off the moons of Jupiter, and get a signal back, and we can determine the orbit and size and so forth of the moons. But radar dissipates quickly, and we would have a hard time doing that. For example, if we wanted to measure the motion of stars, you can't do that with radar. What we can do is do parallax, and let me illustrate parallax. Imagine it's June in Denver, and we take a picture of the sky. And we wait 6 months and take a picture of that same sky. We're looking at that spot on the sky from two different vantage points, because our planet has moved from one side of its orbit around the sun to the other. If we put those two pictures together, we have essentially a stereographic picture of that spot. And we all used, we're all of the right age to have used the clicker, what was that called?
Viewmaster.
Viewmaster. You had that little circular disc, and you saw things in stereo. By seeing it in stereo, you can get the distance. So that's a technique for measuring the distance to the nearest stars, because Earth moves around its orbit, and we can exploit that, and that's called using parallax. But that has its limits as well, and you'll see here, that's good out to about 1,000 light years. So we can look at nearby stars in our galaxy, but not beyond that. There's another technical thing here, but what's really important is this thing, Cepheid variable stars. So there are stars that have a periodicity to their brightness. I'm not making size here, I'm making brightness, sorry. So there are stars that get brighter and dimmer and brighter and dimmer, and Henrietta Leavitt, a pioneering woman astronomer, figured out that the dynamics of what's going on in those stars means that the period of their oscillation is related to their brightness. So this is important for the following reason. If we went outside at night and we measured the brightness of a headlight of a car, and we used a camera or some instrument to measure that, we can tell how far the car is away from us. And so when the car goes, somebody drives the car off in the distance, we measure the brightness when the car is at a distance, and we know how the light intensity varies with distance. It depends on the square of the distance. So if we know the inherent brightness of the star, and we measure the brightness, we know how far away it is. And Henrietta Leavitt showed that Cepheid variables get dimmer and brighter, and that you can relate their inherent brightness to the period of their oscillation. So that becomes a standard candle. If we look at Cepheid variable stars, we can tell how far away they are. And remember, we also have the tool of measuring velocity using Doppler shift. So Cepheid variables are extremely important. And then exploding stars, certain kinds of supernova events, of stars that age to a point where they're unstable and they explode, those are now well understood, and a certain subgroup of them are standard candles. So using these techniques, we now have a way to measure the distance to the star and its velocity away from us. So, and we'll use those facts in a second. Now, speaking of galaxies, Messier, who was a French astronomer, spent a large part of his life observing galaxies. He didn't know they were galaxies. He thought they were planets. Because in the 1780s, the concept of galaxy did not exist. He drew pictures using crude telescopes. He drew pictures like this one. This is Andromeda, as viewed by Messier. This is actually his drawing, and it has this kind of light highlighted area here and a bulge in the middle, and then two little neighbors. And here's what it really looks like. This is a Hubble picture, and there are the two neighbors. So his drawings were very accurate, and he produced this catalog. So we will refer to the Messier catalog like M51, which is unfortunately covered up by the words. M51 is a particular galaxy named by Messier. And by the way, those of you who've been to Paris have been in close proximity to where he made his observations. You could not do this today because city lights, but right at the Sorbonne is where Messier had his small telescope. And the skies were so dark that he was able to draw all these 110 different galaxies. Hubble, now we come to the really important part of this. Edwin Hubble, in the 1920s, is observing galaxies and classifying them. So he noticed, and this, I believe, I put a question mark, but I believe this is his hand-drawn depiction of the categorization. Again, this is sort of like a family tree related to galaxies. Remember, I showed you the family tree of stars, the Hertzsprung-Russell diagram? This is what Hubble drew for galaxies. Ellipticals, clouds, kind of a fuzzy ball, no obvious structure. But then we have these spirals. We'll be seeing these all the way through all of our conversations. Spiral galaxies, and some of them have this additional feature of having a bar across them. So that was, Hubble was taking photographs with a fairly modern telescope in the 1920s, making these observations. Here's a cartoon depiction, a little clearer, with examples. For example, here's a spiral galaxy, and here's a very nice spiral bar. So these galaxies have been categorized. And this is yet another version. This is actually a photograph of an ancient barred galaxy.
What are we?
Oh, we are this. spiral with arms, looks like an octopus spinning around, probably as a result of a collision between two galaxies. And that's why I mentioned, a few minutes ago, I mentioned computational methods where scientists build a galaxy and another galaxy and let them pass through one another. The stars themselves do not collide. I mean, stars are pretty far apart on the scale of the size of a star, but the gravitational effect of two galaxies passing through one another produces this kind of effect. So we probably, I mentioned our galaxy is maybe born 7 billion years ago. Somewhere along the way, something else passed through the neighborhood.
We just discovered 7 billion-year-old stardust on Earth, or so I read.
Yeah?
Is that from perhaps that?
Don't know. I'm not familiar with that. So once again, here's the categorization of different kinds of galaxies. And you'll see some of them have bright spots in them, like right there. Those are solar nurseries, really bright areas where there's been a lot of gas and dust has collected, and the galaxy is birthing new stars. This is M51, which is Messier's numbering scheme, and it has a neighbor, and the neighbor is feeding it. So this thing is rotating probably every 200 or 300 million years, and along the way it's drawing, its gravity is drawing gas and dust out of this neighbor. The reason I showed that is that's an example of a galaxy where we're looking at it as in its maximum size. Here's one where it's tilted. So we see some tilt here, so the galaxy doesn't look circular, it looks elliptical. And then here's one where we're looking edge on. So when astronomers look at these things, they have to try to determine, be careful about how they're looking at it. And notice this one has this dark area here. That's called a dust lane. Yes?
Why are galaxies shaped like a pancake instead of orange?
That's a good question. If we go back here, these ellipticals are shaped like a sphere. There's something about how they formed or how they are aging where these arms were eliminated.
You mean like a rugby ball
Yes,
around?
yeah. So these originally these were called nebulae, clouds. Just a collection of stars, and these are the oldest galaxies that have that feature. So it's possible, in fact, there's a title here, it says rounder appearance as you go left. So this is like some kind of just a cloud, just random collection, held together by gravity, but without all this structure, the arms and so forth. And so it may be that all galaxies are born that way, and if they never have a collision with another galaxy, they just don't have spiral arms. But if they have one encounter, spiral arms form. And the spiral arms are where you see the stellar nurseries. These bright areas here. And one last thought about that. As far as we now know, the center of every one of these galaxies has a supermassive black hole. Our galaxy has a black hole in the center that has a mass about 4 billion times bigger than our sun. And it's just down there consuming whatever wanders into its neighborhood. So we have different views. And here's how the galaxies look different in different wavelengths. So if we look at, this is one galaxy, this is all the same galaxy, here viewed with radio astronomy. And this galaxy has a collection of radio sources, groups of stars, some of which are pretty intense right there. And that's what radio astronomers see.